welcome to this session in MRI Together. So I'm Hamid Haroon. I'm an MRI research scientist at the University of Manchester, where it is right now Monday lunchtime. And yeah, welcome to everybody from around the world to this session. So this session is on quality control mechanisms. We have some brilliant speakers. Unfortunately, one has had to not be able to join us today due to personal circumstances, but our other three speakers, I'm sure, will make up for our loss. So it should be a great session. I've got some announcements to make before we get started. So first off, the session is being recorded and broadcasted live. Transcriptions will be made available on YouTube. And please be aware of the MRI Together Code of Conduct. So please have a look at the session content on the program for other sessions you'd like to join. Questions should be asked in the Q&A box on the side of your screen. And yeah, put your question in there, and other people in the audience, please upvote questions that you would also have liked to have asked, but have already been asked. If you vote for those, then there's more chance that I will choose those to be asked to the speakers as we go along. So we'll have a talk and then a little time for questions straight after that. No question is too simple or silly, and all ideas are welcome. So please ask, and our speakers will be very happy to answer anything. And yeah, the questions with the highest votes will be asked to the speaker. So after the session, please do go back to the program and find the next session you'd like to join. And there is a session every 5 hours, even less than that, actually. So we were going to start with Francesco, but Ariella, would you like to go first? Can we hear you, Ariella? No, I think we are still having problems with Ariella. So let's go for Francesco. And Francesco will be talking about basic principles of decentralized science. Sounds awesome. Sorry, that's not the right one. Why you could and should pre-register your MR method study. That's the one. All right, Francesco, over to you.
All right, thank you very much for the introduction, Hamid. It was a really pleasure seeing you. So I will not be sharing any slide today. If you can make my face as big as possible, because you guys will be seeing a lot of me in this presentation. So I will think, okay, this is gonna be super boring. Daniel, can you make me big, or am I already big? I don't know. In any case, I will. Perfect. This looks good, because of course I don't have any slide, but something will appear at some point in my talk. So first of all, I would like to thank Sophie, Mo, Nico, Daniel, Yang, and Hongfu for the invitation, for organizing again MRI Together, which, as you know, has a very special place in my heart, and I'm really, really glad that you invited me. So today we are going to talk about this, why you could and should pre-register your MR method study. So this sounds really boring, but hopefully it will not be too boring. So I made a poll on Twitter. Actually, it's not a poll. I just asked you a question, whether you could guess what I was going to talk about. So let's see, open question to you, the audience. How good are you at holding your pee? I didn't even know that this was a skill, but well, consider this a little bit. Are you good? You have to rush into the bathroom, or can you hold it? You cannot hear. Dominica cannot hear anything, but I am unmuted. Can anybody else hear me? If anybody can hear me.
Yes, we can. I can certainly hear you.
Yes, we can hear you.
Perfect. So sorry, Dominica, I think it's on your side. You will not see the slides. You will only see these nice props like this. So have you considered how good you are at holding your P? So what if I told you that actually how good you are at holding your P is not related at all to how good you are at managing money? Now imagine you are an editor who might be good at holding their P. Would you publish this paper? If I come to you with a paper saying, look, I investigated this. I thought, let's see how people are good at holding their P and how good they are at managing money. And I found that, yeah, it's actually, there is no relation. Would you publish it? So I think this would just go straight into the bin. Actually, yeah, it's not that simple, because it turns out that there is a published paper. And it turns out that the better you are holding your P, the better you are with money. And this has a very nice fancy number there, a 0.03 p-value. So, of course, this is a finding, and this was published because, I mean, pretty exciting. You can hold your P and you can be good with your money. I'm not saying that this study is bad. This study is for sure good, but it's an example of something that if it hadn't had this very fancy 0.03 number, most probably wouldn't have been published. So what is the problem here? If you have a p-value of 0.05, then you win your publication. And if your p-value is 0.05 or higher, then there's a good chance that your paper goes into oblivion. So what is the problem? Okay, let's talk statistics a little bit. I'm not a statistician, most probably neither are you, but let's just take a normal distribution. This is just a normal distribution. I just generated it. There are a number of points here. And we just divide it in two distributions. So just randomly take two samples of this distribution. So now we do a t-test of this distribution. And, well, the p-value of this t-test is 0.99. Okay, we just throw away this paper. Let's take the same distribution, actually a different distribution, and let's do another random sampling of this distribution, and let's repeat. So I did exactly the same thing. I divided the distribution in two. Now I do a t-test, and what happens? Ta-da! There is a very, very small p-value. It's even lower than 0.01. So I can get my PhD with this fancy paper that says that whatever random numbers can be different from each other, which is a very cool finding. So the point, as Penny Golland said this morning, the value of P005 is true at least 5% of the time. This is actually by design. So once every 20 studies, you will have a study that gives you a significant answer. So by the way, you can find the code here if you want to see how I did that. It's not the best code that I've ever written, but it kind of works. So if you keep running experiments, some of them will eventually turn positive. So you can go and try a bunch of things, and then you only keep the ones that give you the result you want. Again, great mind thinks alike. Penny Golland already showed you this website where you can find the significant correlations between things that really have nothing to do with each other, but, well, they're significant, so in principle they could go to a paper. Per capita consumption of mozzarella cheese with civil engineering doctorates awarded. Well, you can find causality there if you want to try. Or this other one. So this is not something unknown. I mean, this is a clearly characteristic of statistics. And this was actually already seen 20 years ago, or almost. Now it's 2005 by Ioannidis. It's probably the most seminal paper in our reproducibility field. 3 million views. You see, it's actually pretty interesting. So this is a bit problematic because what we are trying to push a product. Imagine you are Novartis. You're a big pharma company, no? And you have a new drug, and you're going to test this drug, and you want to say that this drug is better than another drug. Okay, then you run a study, say that's not really better. Okay, let's try another study. So try another study, see what happens. Eventually, you will get a positive result. You can say your drug works. You can publish that, and you can sell it. And this can be just due to pure statistical fluctuation. So just repeating the same study over and over at some point will give you a positive result. Oh, and this is just statistics, but of course there are a lot of other tweaks that we can do. So, and this is a very famous paper, also cited many times. And this happens that some tweaks can happen at every point of the scientific process to get a little bit a better result than we already have. And sometimes they don't even require a lot of malice. Just a little bit of ignorance is enough to just go and tweak your results so that they're better than they actually are. Clear example, the Texas sharpshooter. You just shoot at a barn, and then you draw some targets around circles. This is called arcing. So you are first seeing the results and then saying, okay, this is significant, so it must mean something. Let's just keep this one and justify it and saying that this is what we were trying to measure all along. A lot of other things were already treated last year in MRI Together. There were 2 nice hand-on sessions called the Whitehead's Guide to P Hacking, and I really encourage you to have a look at them if you're a little bit into statistics. So I want this to be a conversation. I hope that you realize that this can be a problem. No, so you have a drug, or in any case, you have your idea that you want to publish your science, but it seems that you really need this significance to be able to publish it. Unfortunately, this is how things work at the moment, and we want a positive result. Instead, what the reproducibility movement and us we are trying to do is really need to shift the focus from the positivity of the result. So in the end, we don't really care if holding your P makes you good at money or not, as long as your study has been done well. So you first, before beginning the study, you say, okay, I have a question, and is this question relevant? Would I want to know the answer to this question, even without knowing even whether it's a positive or negative? So we need to shift the focus there to the relevance of the question and the robustness of the methodology. So is my study enough to actually show that if there is a relation between the variables, then this relation appears. So we want to make sure that whenever we want to test a hypothesis and demonstrate a hypothesis, we have some rigorous planning here. And also not that, once we have executed our study, which is very well planned and all the data are collected and analyzed, we want to make sure that the results are public, because we don't want to be in the situation of the pharma company that then just withdraws the results that they don't like, so that we have these nice drugs that seem to work perfectly, but they actually do nothing because it was just a pure coincidence. So we have some tools to do this. One is pre-registration. What is pre-registration? So it's a public declaration of a study. It means that we are going to a website, we are filling in a form, and we are saying to the world, we are going to run this study. It is not peer-reviewed. It's just something that I do and I announce. And it's not a publication. So it's just filling a form on a website and everybody can do it. Sometimes it is required in some cases of clinical trials, explicitly because they want to avoid that if you have a drug and you give misleading results, they require you to do this. I apologize if the font is a little bit hard to read. I realize on the other monitor work better. So I would say the pre-registration is a tool for the society, because pre-registration does not help against this publication bias. Pre-registration will not get your results published. It will just say that you are going to run this study with these specific parameters. And you have then to adhere to this parameter. But no journal is required to publish your pre-registered work. So you pre-register work, but it might never publish. So it might still have problems with publication bias. You might not find a journal that publishes it. So if you are, say, Novartis that is doing a phase 3 drug trial, then yes, someone can go and find your pre-registration and said, but yeah, you tested this drug in 100 or 1,000 people, and what happened to it? Why didn't you tell us what happened? But if you are like me, nobody that just wants to run a small study on 10 people, I mean, nobody is going to dig up your pre-registration and say what happened to this. So it will also not happen in your career. It's not peer-reviewed. It's basically counts nothing. So pre-registration can be done in a few different places. You have clinicaltrials.gov as predicted, OSF pre-registration, and it's something very good because it gives you a plan. It helps you having a plan, and it also tells the world, okay, well, I'm going to follow this plan. So it's something very important in general whenever you want to test a hypothesis. But as I said, it will not help you against publication bias from the side of the journals. There is another tool, and this is a little bit more controversial, if you say. Well, I didn't think it was controversial. I tried advocating for it, and I found out that many people find it controversial. You tell me if it's reasonable. And it's a register report. A register report is not a pre-registration. So it's a manuscript describing, oh, I'm sorry for the font, describing the methodology and the data acquisition, but it's a manuscript. So in a manuscript that only contains the methods and the introduction. It is peer-reviewed, and then the important part is that acceptance in a journal is guaranteed. So if you pass this peer review at this first stage with the introduction and method without the result, then you're going to publish your data. And it's not public, so you don't have to disclose anything with it because it's only confidential to the journal that accepts it. And this is a tool to protect the authors from journals bias. So if a journal only publishes positive results with negative reports, with the register reports, we can make sure that whatever the outcome of your study is, it's going to be published. Of course, not all journals accept that. But what happens without register reports? So I'm telling you what they do. Why would anybody want to have the register reports? So without the register report, you have uncertainty of publication. So you run a study and you gamble. If it's going to be positive, you're going to publish it. If it's going to be negative, then it's going in the drawer, and you're going to waste all your time and resources and money, and you're also doing human experiments, and they result in nothing. So this is a disincentive towards large studies, because you're not going to spend resources to run a study on 1,000 people if you think that it's going to be put in a drawer. So you run very small studies instead. If you want to write a register report or know a little bit more about register report, there is this recent paper that I encourage you to read. So we have these two tools. One is pre-registration and one is register reports. Let's keep this in mind. So how does this relate now to MRI methods? I promised you that we're going to talk about methods. We still have a few minutes, so let's do that. What kind of study have we described so far? So these tools are applicable to studies that try to demonstrate something. So for example, is holding a P an indicator of how good you are with the money? So you say yes or no. So there are some exceptions to this, but mostly we want to demonstrate something. This is a hypothesis-driven study. Usually a hypothesis-driven study tries to give a yes-no answer, and they use inferential statistics to reach a conclusion. And this is where p-values come from. So 0.05, lower yes, higher probably no. On the other hand, if you're only describing something, so you say, I want to know how long on average a person can hold their P, then this is not a hypothesis-driven study. You're just saying, okay, it's 5 minutes, so it's 1 hour. So this is an exploratory of or even better to say observational study, because in the end, you don't care what the result is. No, you just want to have a number. If it's high or low, in principle, it doesn't really matter. This is what you want to investigate. So about MRI methods, what are these? Are they hypothesis-driven or are they observational studies? So when you when you develop your method, do you want to demonstrate something? I would say yes, because a method that you develop is in general something that you want people to use, and it serves a purpose. So you want to demonstrate that your method works. Either it works or it doesn't work. So it's a yes or no answer. So you are demonstrating something. Usually you acquire some validation data, some quantitative metric, and says, okay, if this metric is good enough, then it works. If it's not good enough, it doesn't work. It might not be explicit, but it's always there. Do we see a bias against negative results? I would say yes, and we will see an example in a moment. If the method is not of desirable quality, it will not get published. If there is a bias against negative result, do we have a push towards making our results positive? I would say yes. No, I mean, we probably know what happens. We have a look at the images, and some images you say, okay, but this image is not good. Maybe we should just remove it from the analysis because we have artifacts. I'm not saying it's good practice. I'm not saying everybody does it, but it's not inconceivable. And do we see a trend in small sample sizes? If you read some papers of the field, I would say yes. So I read a recent issue of MRM. The median number of subjects in this journal was 6, and many methods were validated on just 3 subjects. Well, this is clearly an example that is not convenient if you have a new method to do a very large validation cohort, because if the method fails in your large validation cohort, then you will not publish it. And if you look at +1 about methods, even they recognize the importance of validation. And if you see here, the tools must demonstrate that the new tool achieves its intended purpose. So it's explicitly putting a bias against negative results. You're saying we're not going to publish negative results. Imagine if this was a drug. Instead of being an MR method, imagine if this was a drug. Would it be acceptable to say, we are only publishing a paper about a new drug only if the drug works? Isn't it the situation that we had seen exactly in the beginning? So what are the implications? So let's chat a little bit about this. What happens when you want to develop a method? You have a new idea, and you go and search the literature, and you don't find anything. So success. It might mean that nobody had this idea before, you are the first. Or in our current culture, the idea was already tried and it actually doesn't work. And maybe it was tried 10 times and it never worked, and nobody published it. So you're going to publish, you're going to try for the 11th time, and it will also not work. And what happens on the other hand, if you see a proposed method and you see, okay, it was validated in 2 subjects, are you going to invest money to try to re-implement the method so that you can do more research on it? Or you say, okay, let's wait until someone else does it because 2 subjects, okay, it might be promising, but I'm not going to invest time and money in something that might be unreplicable. So I think that from these points, there is no reason why method development research and MRI methods specifically should not be a perfect candidate for pre-registration. And indeed, nobody stops you from pre-registering your study. This it's a very good idea. You can be then rigorous, you can establish your sample size, you can guarantee that your validation was fair, and if you don't want to disclose the details of your method, the pre-registration allows for an embargo period. So you have 1 year, then you pre-register it, and then you publish it properly and say, okay, this was actually pre-registered and time-stamped and everything. However, this is only a part of the problem because you don't get guarantee of acceptance. This is not a publication. Pre-registration is not a publication. So it actually makes your study riskier because then once you're pre-registered, you have no room for actually tweaking your results the way you want. It's either positive or negative, and then you might just not publish it anymore. So what I'm arguing for, and this is something new, is that we should try to have registered reports in our community too. Pre-registration is only half of the story. Registered reports is what then will allow us to overcome the problems with small sample size and uncertainty in the publication and the erasure of negative results. Remember, your methods, your MR methods, are not very different from a new drug. If you have a new method that provides a diagnosis, this will influence the therapy just the way as a new drug will do. So these registered reports would actually guarantee some fair and robust validation and a higher impact for the method. So it's not just that it's the right thing to do, it's also convenient. You can have, you can perform validations on many subjects and have a very high impact paper published. And I think as a, let's say, preachy note, as if the whole talk hasn't been preachy so far, we are also in the business of doing science. We are producing knowledge and we are not selling a product. Our interest is that what we published reflects as best as possible what the truth of the reality is. So it should be a slam dunk. I thought it was easy. Unfortunately, the registered reports are not accepted in our field. Nature Methods does accept register report, but not for new methods explicitly for some reason, I don't know. I tried convincing the editorial board of MRM to launch a pilot phase to try register reports in our field. I told them more or less what I'm telling you now, and unfortunately, they were not convinced. So we don't have registered reports in our field. So I think they would be a good solution. Pre-registration is of paramount importance, but it's only part of the solution. And I think the register reports would get us there. They would not make science perfect, but they would be a step forward towards a more robust, reliable, and reproducible science. Okay, this is what I wanted to say. Thank you very much for your attention, and I hope you liked the talk.
Thank you so much, Francesco. That was a brilliant talk. Well done. So yeah, I cannot hold my pee, and I am not good with money. So maybe there's something in there.
Right.
If anybody has any questions, please put them in the Q&A chat. So that would be amazing. And we could put those to Francesco. So how does pre-registration, Francesco, how does that avoid us making spurious correlations?
Well, it doesn't really. So it's, as I said, it's only part of the solution. But at least if you pre-register your study, you make sure that you go and publish what you actually went and test for. So you cannot, if you say, I'm going to see if my T1 value that I get from my own quantitative method correlates well with the T1 method from another method, then this is what you're going to show. And you're not going to fish for other correlations between other metrics that you can make up on the spot after you've seen the results. But of course, you can run your study 20 times and nobody stops you from doing that, even if it's pre-registered.
Sure. Any other questions? Come on, somebody's got a burning question somewhere. Nothing's too simple. Things too silly. Ask whatever you like.
You can find me on Twitter, or you can probably find me on GatherTown as well, and you can insult me privately.
Oh no, no insults, please.
Not publicly, at least, please.
Okay, so somebody says, thank you for the great talk. I kept thinking about pre-registration as a protocol publication, so just confused about the two. Yeah, what's the difference, Francesco?
Yeah, the registration is public, but it's not peer-reviewed, so it's just your intent. It's basically equivalent as putting your research plan on your website. It's it is public, but it's not a publication. You cannot really put that in your CV. Nobody will care, because you might end up not doing the study, or it might be completely flawed and it's not peer review, so nobody can check that.
So somebody's made a comment here that registered reports seem to disrupt the usual order that science is done in. Is that one of the main oppositions to their use in MRI?
I don't know what the usual order is. Usually I have a hypothesis and I come up with a method for testing it, and then I publish the result. I mean, this for me is the usual order. If I do it with a method, I have an idea of a method. I try to do some preliminary work on some phantom, and then when I'm reasonably sure that this method has some value, then I will do the validation and say, okay, let's see if the method actually works in the intended population. And this is something that could be applied for MR methods, meaning that once I have a hypothesis, so this is the method I want to test, and my hypothesis is that it works, then I can do the proper validation. Otherwise, if you want to specify better about the usual order, I would be very happy to discuss about it.
Great. Okay. Thank you, Francesco. Please stay on the stage, Francesco, and we'll continue this conversation hopefully a little later. So our next speaker, do we have Ariella? Is Ariella around? Daniel, can you tell us, please?
Daniel's just pasted chat. Oh, second, apparently.
Your second. Right, Gareth, here we go. So Gareth is going to be talking about considerations for data harmonization and sharing. So great.
Okay, hello everybody. Thank you for the invite for doing this. I didn't manage to do anything as clever as Francesco with all those things that appear in his background, so you're getting simple PowerPoint type slides, if I can manage to share the right screen. So just one moment and I will put those on screen for you. Aha, stop sharing. I am trying to work out how to get around the message that I am seeing on my screen to say stop seeing an infinite window. I think we're seeing the right things. Okay, so going somewhere totally different from where Francesco's just been, I'm going to talk to you a little bit about how do we actually collect data. And he made the point about essentially about power calculations and sizes of data and things like that, that the reproducibility is very important to have a big enough sample set. One of the ways that is often done is through multi-center studies and through data sharing. So I'm going to go through some of the background and the technicalities on these things. Just to note, not directly relevant to this, but I do get some honoraria from GE Healthcare. So the question is to why am I talking in this session? So what I'm going to be talking about is setting up multi-center protocols and procedures and studies, and then some of the legal and ethical issues about consenting for data sharing to try and get these bigger studies off the grounds. I'm going to talk about measurement systems a little bit. What is it that we're trying to do? What do we need to get reproducible data? I'm going to talk a little bit about protocol standardization with some examples from the things that I've done. And then I'm going to talk about ethics and data protection and some general tips and tricks if you end up doing these things. You will note that there are 57 slides in this presentation, and I'm not going to get through those in about 20 minutes or so. So I've pasted into the chat the details of the presentations as PDF so that you can follow all the boring bits afterwards and follow up the links and so on. And I'm not sure, it isn't Nicholas now who's going to be speaking, but I'm not going to talk about the technical aspects of data storage and so on. I'm leaving that to the following speaker. So why do I say I'm going to start off by talking about measurement systems? Apart from the fact that this is a good point to point out that there are lots of things that you need to standardize, and just even silly things like British and American spellings can make problems. So think about harmonization. But for multi-center studies, data reuse, etc., there are lots of reasons why you might want to do that, and it's usually to do with faster recruitment, larger total subject numbers, less reliance on particular centers, just generally making things more generalizable. And the downside of all of that is always that whenever we do things where we start sharing things and trying to mix and match across studies and sites and centers, we end up with lots of variability. Why is that an issue? Well, there's some sort of variability both between and within sites is inevitable, and we want to make it small, which is hopefully fairly obvious. And ideally, we want to make the inter-site variability similar to the inter-subject variability, such that it's the differences between our participants that's dominating what's going on. So it's the interesting biology, or even the interesting sample variability if we're not doing in vivo studies. It's the thing to do with what we're studying that we want, not the effect of our scanner to be the major effect. Just some definitions, I won't over-labor these, but that variability can affect both what we call accuracy and precision. Accuracy is how close you can get to the true value. So if you're aiming for the bullseye in the middle of a dartboard, it's how close you get to the center. Whereas precision, which is also sometimes talked about as reproducibility or repeatability, is how much scatter you get. Can you get the same answer twice? And in terms of MRI in particular, we're nearly always talking about reproducibility as opposed to repeatability. And there's a couple of definitions there that actually come from Wikipedia. But reproducibility is about how close we can get to the same measurement again and again when the conditions change slightly. And that's when we perhaps do a rescan, or we scan on a different day, or we use a different scanner, or we mix and match between scanner vendors or sites. All those things affect reproducibility. Repeatability, which we don't usually get to do, is what happens if we manage to make a measurement twice in exactly the same conditions. And so just to stress a bit of terminology, we're interested in accuracy, precision, and reproducibility. And typically in most of our research studies, reproducibility is the thing that we care about. We want to get measurements that give a very similar answer. And actually, I hate to say this as a physicist and as a person who works in quantitative MRI, but actually we often don't really care about the actual numbers and the units as long as we get the same one whenever we measure it. Because the thing we want to be able to do is distinguish patients from controls, groups from each other, responders from non-responders. We want to be able to pull apart those differences at a group level, and that means making the variability within our groups as tight as possible. That means getting our reproducibility up. It's also worth noting that it's a bit of difference depending on whether we're doing cross-sectional or longitudinal studies. In cross-sectional studies, in particular, control subjects are essential if you want to be able to tell allow for intersite effects. No matter what you do, this is just one of my little tips. You need to include site as a covariate of no interest in your final analyses. There will always be differences between sites. In longitudinal studies, you have to think a bit about the fact that adding extra sites adds extra variance to your results. But actually, there are also both intersite differences and time differences. Your scanner may drift over time. All your scanners may drift over time, and they may drift at different rates. So you need to think about how you set up your studies and how you make sure that you are going to allow for all these effects. And this is one of my tips and tricks. Paper that I strongly recommend you have a look at, mainly because of this quote, which is right in the introduction, I think. Despite numerous technical treatments, analysis of covariance, which is essentially what we nearly always do when we're doing big multi-center studies, in fact, lots of studies, it said it's widely misused to dealing with substantive group differences. So you'll hear people talk about, I controlled for age, or I controlled for gender, or I controlled for a site difference. And often it is not possible to do that at the analysis stage. You have to think about balancing groups and things at the initial stages. So do at least skip read that paper, because it's a really common mistake to make. Other thing to note is that those Wikipedia definitions I gave you were of the accuracy or precision of a measurement system. And that involves all elements of the system. And that's not just the machine itself, but it's how we collect the data, it's how we analyze the data, and what we do that might mess up the data as we go along, the human intervention. So I'll be focusing on the acquisition side of things for the next few minutes, but the other two are quite important. Oops, and that was not supposed to show up quite yet. My animations are wrong and I can't get rid of that. So I will read what it says in that slide behind the poor design of experiment ships six knowledge. It's a little example on the left-hand side there of some differences between free surfer analyses of some structural data, and it's a relatively old 10-year-old paper now, just showing that simply changing software level, and the same paper also shows the difference between changing CPUs, changing operating systems. All these things can make subtle differences to our results, so you really do have to lock things down. Things like the floating point calculations and libraries used can make a difference to the results at the level that we are often looking at things. And it's a little hard to see what it says on the other side of there, but we also need to think about the human interaction, how you prescribe slices, exactly how things are adjusted on the day, what instructions you give to somebody if they're doing an fMRI task, how you ask them to lie still, how do you ask them to keep their eyes open or closed, and so on, all make a difference. Just to say, again, stress some intersite variability is inevitable. Mixing scanners always makes things worse. But you need to just basically think about protocols and standardize across whatever sites you're going to involve, assuming you're doing a prospective study. And I'm just going to go through some examples of some of the studies I've been involved with and the sort of things we had to think about. So I've got a few slides here just giving you some background on these studies. I'm not going to talk about the results of the studies, and there's lots of details on the slides. And that's largely just to stress that these things get complex very quickly. So one of the studies I was involved in many years ago started back in 2007, was this so-called imaging study. So you're looking at imaging and genetics in what were then 14-year-old children across Europe. That meant scanning these kids at a number of different sites with a range of different scanners. And it was quite a complex protocol. It had some structural MRI, some task-based fMRI, some diffusion imaging, and various other things. And then it's had multiple follow-ups since then, most recently in 2022, at their age of 22, which is a couple of years ago now. That was followed by this so-called CVIDA study, slightly less participants, but now across India, trying to look at the differences between different cohorts there and compare them to the imaging cohort. It was a different study design. It was in different sites, obviously, and it had different scanners and different software levels. But again, it had some very similar structural MRI, resting state, fMRI, and some diffusion imaging. But that study was trying to be directly compatible with some aspects of the imaging study and directly compatible with 2 other ongoing UK studies. But they also wanted to link into a study in Germany. They wanted to piggyback to some extent on the ABCD study in the US. And since then, there have been 2 more studies which have tried to use these protocols again. And the main reason for stressing all of this is just that things get very, very complex very, very quickly. And so you need to think about what might happen in the future when you start setting these things up. So what we did when we set up Imogen was to start thinking about how do we standardize some of the major things we wanted to do. And these were at this point fMRI and structural MRI. And it's relatively easy to match up the fMRI sequence parameters, TEs, TRs, matrix sizes and things. It's a bit harder to do it for structural MRI because different scanners have different capabilities, but there were some protocols that we could already piggyback on. So we started with what seemed like reasonable best guesses to things that might work across all these scanners. We actually, at the time, ruled out both perfusion imaging, which we were interested in, but which really wasn't possible given the differences between manufacturers at that time. And we also ruled out doing spectroscopy, which we thought would be interesting, but again, was just too hard to standardize. So what we did, and what I'd recommend if anybody is trying to do these sort of things, is we initially sent out an email and just said, what scanner do you have? What coils do you have? What software do you have? Who's the person we should talk to about this? And then we pulled together people from all those sites to try to lock down parameters that were possible on all scanners. We also tried to think about the hardware that was necessary. How do you provide uniform paradigms for fMRI? And then we moved on from the fMRI onto the structural scans and did the same thing again. And having finally locked things down, and I'll show you some of the changes that we made as we went through the iterations with physicists, we then asked sites to do some scanning, some test scans for us, checked all those, and set up some site visits where we physically went around to each of the sites to finalize things. Again, don't want you to necessarily focus on these. The details are in the slides if you ever want to. But fMRI, we were aiming for the highest common factor, not the lowest common denominator. And that meant thinking about what brain coverage we could get on all the scanners and thinking about some things like the positioning of slices. For our structural scans, we looked at various different possibilities and actually decided that basing things on the ADNI MP range scans was going to be probably the easiest thing we could do. And then things that you might not think about, but things like our diffusion scans, we had some wonderful protocols, but actually it turned out that between the 3 main manufacturers at that time, the only number of diffusion encoding directions that was available on all scanners was 32. So that was the answer to how many diffusion directions we were going to be able to do. If I was doing this today, I probably would want to consider perfusion imaging, and there has been some standardization work there, and there's a URL there. MRS is probably still a bit problematic, and inevitably technology has moved on, and all the things that might be different between scanners include things like multiband and compressed sensing and deep learning reconstructions and all the other things that have come along in the last few years. Just to show you that standardization is worth doing, though, this is the best image that 2 scanners, it's actually a GE scanner on the right-hand side, and I can't remember if it's Philips or a Siemens scanner on the left. These were their two nearest equivalent images, and you can see visually they just don't look the same. Here's an example after we'd taken some standard protocols, the ADNI protocol, and tweaked it a little bit, that you are able to get things if you have enough physicists involved who know the details of exactly what matrix sizes do and what loops happen in what orders and where each pulse happens. you can get images which look very similar between the scanners. There are still some differences. There are differences due to things like the filters that manufacturers apply, which they often regard as proprietary and which it's quite hard to match. For fMRI, we looked at all sorts of things about the angles that we could put our images at, whether or not you do what's called top-down phase encoding, whether we had A greater than P or P greater than A phase encoding. There are lots of different things that we looked at there. And again, we were able to show that within reason, you can get quite good matching between Philips, Siemens, and GE, which are the three manufacturers we were interested in there. And it's interesting that you do still get some differences, though, and we were able, with the physics, to understand why the GE scanner, in this case, looks different from the other scanners, and that is not something that is going to cause a problem for the fMRI results. And just another thing on filtering, showing how important it is to match all sorts of things you might not immediately think about when you start doing these standardization efforts. Slight aside, a lot of these things required us to use local modifications and works in progress, and there are some regulatory issues involved. And if you're in Europe, that mainly revolves around so-called CE marking. If you're in the US, it's mainly about the so-called 510K pre-market clearance, but it's all the things that your scanner manufacturers had to go through to show that everything is safe. The UK is currently, thanks to Brexit, an outlier here where we have a whole load of things where we do endeavour to overlap with the EU at the moment, and I will leave anybody who wishes to know about that to look at that. But the upshot of it is that an MRI scanner, when you are using it for research, may or may not be classified as a medical device, and you may or may not therefore have to obey a lot of regulatory issues that relate to the way medical devices are regulated. So have a look through the regulations for your own country. If you're doing research, probably this doesn't directly apply to you, but it's still quite important. And it's all about making sure that you have thought about all the safety issues of any modifications to protocols and any modifications to pulse sequences that you make on the scanners. So think both about anything you do locally and any works in progress, any patches, anything else that might take things outside the CE marking or the approval for your country. I'm also going to talk briefly about quality control, just mainly to say that this is important and you can use it both to check stability over time and see variabilities on a particular scanner performance over time. You will not very rarely manage to do QC checks in time to say, we need to change what we're doing. Oh dear, we should stop scanning on this day. So you're usually looking at QC data retrospectively. And one thing, actually, I'd be quite interested to hear what the other speakers think about, and Francesco in particular. I think that this is a particularly good way to allow an unbiased exclusion of study data where you know that there was a problem it's shown in the QC on a particular date or a particular site. It's a way of being able to exclude data from further analysis without being accused of cherry picking and without coming up with the result that you had particularly wanted. You do need to think about the cost of phantoms, which are excessive, they're very high, and how you get those phantoms to sites in multi-center studies. And what we did in Imogen was use a mixture of the ACR tests, American College of Radiology tests, and some of our own tests. We also did both phantoms QC and some in vivo scanning. And we said that the closest you can get to what you're going to do on your participants is to scan other volunteers and scan them regularly. And we suggested that they did that for Imogen. We scanned twice a year and before and after any upgrades. So you've got some sort of idea of how the scanner performance is changing over time. We also suggested that we do phantom testing very regularly, just so that you can see if the scanner starts to drift or something starts to go wrong, and you can avoid wasting precious time. So that's some, I'll come back to some tips and tricks right at the end, but that basically is how we set up the Imogen and CVIDA studies. Lots of thought about what protocols we do, lots of thought about how we then make sure that everything is standardized, and then some QC to see what the scanners are doing and to allow us to exclude data potentially if necessary. So a bit of a swap now. So ethics and data protection, which applies whenever you're sharing data, both on a prospective study and if you're hoping to use some data that's already been pre-collected. Little bit of background and guidance. So you may or may not have heard of, hopefully have heard of the Declaration of Helsinki. This is the ethics background that underpins most regulations in most countries of the world. Actually, slightly bizarrely, not the US for some very specific reasons. The US used to follow the Declaration of Helsinki and has withdrawn that now, but the principles still apply. This is all about making sure that you have planned in advance, that you know what you're going to do, you know what you're going to do if something goes wrong, that you've got people's consent, you're minimizing risk, and that you're safeguarding both yourself and the research participants. This has been governed more, this has been joined more recently by the so-called Declaration of Taipei, which is looking specifically at biobanks and health databases and data sharing. And this is all about the same issues as the Declaration of Helsinki, but also talking about privacy and confidentiality, dignity, autonomy, discrimination, things that are important to consider if you're going to try to database information. If you're doing something in the UK or the EU, here's some links that you may want to follow. General ethical issues and clinical trial regulations and things which will affect you, and how to really implement those ethical considerations, getting your IRB or Research Ethics Committee clearances, and just thinking about how to make sure that you are doing the best study you can. And then if you're in the EU or the UK, you also need to think very carefully about GDPR, the General Data Protection regulations, which set out some key principles as to how you must try to maintain the use of data, how you process data, how you store data, how you ensure that you are doing this in a lawful manner, but also in an appropriate manner, given what the participants in your study think they have signed up for. And it's worth noting, again, if you're in the EU and the UK in particular, that you need to have what's called a legal basis for doing your research and for storing that personal data that you'll be storing, including MRI scans, etc. This is usually something that's called a task in the public interest, and that's one of the things that GDPR specifically allows data to be stored for. You also need to be careful about having a so-called condition for processing, and that would normally be that it's necessary for scientific research. Again, GDPR doesn't block things, but it requires you to make sure that you've specified why you're doing things. And it requires some safeguards in place, and those include specifically having ethical clearance, thinking about informed consent, and minimizing the data you collect. So some things that are important to think about. There are some links here to what I believe are the latest guidance in the US and in Canada, and I wasn't able to find everywhere else around the world. So look in your own country, find out what the legal guidance is, find out what the recommendations are. One thing very specifically that comes up if you're doing MRI scanning is so-called incidental findings. And an incidental finding is anything that was previously unknown that you uncover. So if you suddenly find that one of your healthy controls has what looks like it might be a lesion or a tumor, that's an incidental finding. And you need to think about what you're going to do about it. And actually, there is no best practice about what you should do about this. So you need to think about it in advance. Are you going to put some scans in so you can actually screen people to make sure that they are healthy controls, if that's what you think they are? And if so, who reviews them? And if you do find something abnormal, what do you do about it? Who's informed? Who does that information, provides that information? How do you counsel people? How do you follow up? How do you pay for any follow-up that might be needed? And also, what do you do if people don't want to be told about an abnormal finding, which is quite possibly because they might, it might be false positive, it might worry them, it might impact on their healthcare insurance, it might impact on all sorts of things. So think in advance about what you will do if you find an abnormality and what you do if you are not able to tell anybody about that abnormality. So that lot was possibly a whole load of, here's a whole load of regulations and I'm not telling you anything. So my main recommendation here is actually you go and look at something called the Open Brain Consent site. And this is has the strap line of make open data sharing a no-brainer for research ethics committees. There's a paper about this that's a preprint is available. And there's a website that provides you with templates and guidance that try to cover things like the GDPR compliance, all the issues you might want to think about, including about the incidental findings, etc. So have a look at the links there. So I'm wrapping up now. Final few tips and tricks. Do document everything. Do make SOPs for everything, standard operating procedures for everything. Make sure everything is written down as early as possible and locked down. And then make sure that everybody uses your locked down documentation. You may need to think about things that you haven't really thought about the fact that things that happen in a different country to yours do not necessarily follow the same regulations. The people there have different genetic makeups. There are all sorts of things that may need to be thought about in advance. Probably the single best thing that we did in Imogen was decide that we would barcode every sample, and every MRI scan would use a barcode such that the details could be entered directly into the scanner. Barcodes, you can download barcode fonts, you can print things in a barcode font, and when you press the scanner at it, press the barcode scanner at it, any USB capable device will see this as a keyboard, so it looks as though you have typed data in. So a really good way of getting data into your scanner. Important to think about follow-ups on these things. Make sure you've got consent for consent. Make sure that you're allowed to keep going back and talking to your participants if you want them to come back. Keep in touch with them, do newsletters, social media. Make sure you can follow them up if you want to in the future. And so I guess the take-home message is data sharing, multi-center studies, lots to think of, but this is possible and it can be very useful. And just so you have my email address there. So I've probably talked for too long there. I'm going to stop screen sharing and I will take any questions if there are any in there coming up in the chat.
Thank you so much, Gareth. That was amazing. Wow, what a talk. So we've got a comment from Penny and similarly Francesco. So describing QC steps should be a compulsory part of our methods description, even if it goes in an appendix. Would you agree?
I agree.
Yeah, cool. Please do post your questions in the Q&A function. It'd be great to have some more questions come through there. So Gareth, do you think there's any role that manufacturers could play in harmonization and other such initiatives?
I mean, the manufacturers often are involved, and the manufacturer's individual representatives are often very helpful with this. There is an interesting sort of dichotomy, of course, that the manufacturers want their scanners to be different because they want you to buy their scanners because their scanner has some feature that isn't available on the other manufacturers' platforms. And so there is a bit of a tendency to end up with a lowest common denominator, something that all the scanners can do. So you do have to be a bit careful about that. Manufacturers are, if you approach them, often very good at giving you those little bits of details that say, actually, that is possible on your scanner. You just have to tweak this or change that or do something else. And one thing we certainly found with the imaging study was that it was very helpful to have people at each site who had their own contact with the manufacturers. Most people will have a site scientist or somebody that they go to. So if I, and you know, Hamid, I typically am using GE scanners. If I go to Siemens and say, tell me all the technical details of your scanner, they're less likely to do so than if I go to a site we are working with and say, could you ask them? And then we all agree that we will keep anything confidential. So the manufacturers, I think, can be useful indirectly, but it's unlikely that they are going to directly support standardization as such. Although things are becoming more and more standard in lots of ways, lots of protocols are now available across the many manufacturers, and sometimes they will tweak their individual products to allow things to be compatible at least.
And just one more question. In terms of harmonization, how important is field strength in that regard? So, for instance, in developing countries, lower field scanners are being kind of brought in, and then other centers will have high field scanners. So yeah, how does harmonization work across them?
So I have to say, I was trying to set up a study. In general, I would want everything at the same field strength. That isn't always possible. And I think the thing would be important if it isn't possible is thinking about the study design. So for a longitudinal study, for instance, that may not matter as much. If you are looking for changes in a parameter that should be visible at either 1.5, 3T, 3T, or on one of these very, very low field strength scanners, then if you should be able to see that change, then probably your field strength is just differences are just adding extra variation to your results. On the other hand, if you are looking at something whereby you wanted to look at something quantitative, like say, you know, a T1 or a T2 value, those values actually fundamentally differ across field strengths. And so it's important to not be doing a direct site A, site B comparison and then saying, oh, there's a difference, and then realizing that that's all down to field strength issues. So I think it's all about study design, and it's nearly always about making sure that you've got anybody who's scanned on a particular scanner is scanned more than once, so you've got a nice longitudinal record of what's happening, and balancing up your healthy controls across all your sites such that at least you can do sort of what I tend to refer to as 2x2 designs. Is there a change over a time that is consistent over all these scanners after taking out the site effect?
Wonderful. Gareth, we've got one question in the Q&A. So in terms of sharing across countries, any ideas of addressing the difficulty of anonymization of brain MRIs in a way to ensure privacy and confidentiality?
So that depends where you're sharing data. I'll try that again. Sharing data from. If you're in Europe or the UK, then the regulations make a distinction between anonymous and anonymized data. And even if you successfully anonymize your data, it is still considered personal data if there is any way to link back to it. So you still need to be very careful about data sharing and have appropriate data sharing agreements in place anyway. But the safeguards that you're expected to do are to try to make it as difficult as possible to re-identify somebody. So there are more and more things available to do things like defacing of scans, such that you sort of crop out turn that way, you crop out this section, avoiding the brain in an automated way. And that makes it much harder to re-identify somebody. You can't simply do a facial recognition on them. You obviously need to remove all the major information from the image headers. And if you have done that, and if you have permissions to share between the sites, then and some sort of agreement as part of the underlying grant funding or the underlying project, then that I would say is fairly reasonable. So strip the headers, think about whether you want to strip the face off, and then still treat everything as securely as possible is probably the best practice, best principle. I will try and find it and paste it in the chat. There is actually something called the UK Anonymisation Network, which isn't UK specific. You can and talks about all these issues for all sorts of different types of data. So I'll try and find the link to that and paste it in the chat.
Wonderful. I think we're going to have to move on now. Well, there's a comment that defaced MRIs are at best pseudonymized.
Yeah, exactly. So they've been de-identified in the headers and they've been pseudonymized. They are not anonymous, so they're still classified as personal data under GDPR. And so they still need to be treated very carefully because they are potentially re-identifiable. So yeah, I would agree with that.
Great, Gareth, if you could stay on stage, please, and we'll hopefully have some more questions and discussion later. Ariella, welcome. Can you hear us? Can you hear us, Ariella? I think we're still having problems, Daniel. Oh.
Hey, can you confirm that you can hear me now?
Yes, we could hear you. Can you hear us, Ariella?
Okay, great. So I am glad my microphone and everything is working now. Unfortunately, there's still a technical issue where when I'm on the stage, I can't actually hear anyone else on the stage. So if you would like to say something to me, please put it in the chat. And if you'd like me to pause for any reason, just somebody wave their arms vigorously at me. I'm going to get my slides up now. And while I do that, I would like to just thank the other speakers and the organizers for bearing with me with all these technical difficulties and, really, adjusting the timeline. Thank you to the other speakers that went first when, not at their specified timeline. That was really helpful because now it's allowed me to actually have a chance to present my slides. So thank you so much for that. Can we confirm? Hold on, let's see if I can make this full screen. Okay. Hopefully there won't be any more technical difficulties. 1 second. All right, full screen. This worked in the green room, I promise. Okay, we are going to abandon full screen. And we'll just have to deal with some overlays. Okay, so I'm going to get started now. And I just want to make sure that I can see the chat in the other window in case any questions pop up. Hold on. Oh dear. I'm sorry about this, guys. It worked in the green room. 1 second. Let me try sharing slides. No. Okay, I think it's actually working now. Okay, great. Awesome. So, but I can't actually see anyone else. Okay, okay, okay. Thank you so much again for bearing with me. Now I can see the chat and my own window. All right, so without further ado, I'm going to be presenting today on the basic principles of decentralized science. My name is Ariella Coler-Reilly, and so for my background, this is who I am. I'm an MD PhD student at Washington University School of Medicine in St. Louis. I study molecular cell biology, science communication, and medicine. And I'm the founder of an organization called Web3 Women in Science. In terms of my disclosures and disclaimers, I am a contributor to organizations called DAOs, which I'll explain in the following slides. Nothing I say here is financial, legal, tax, investment, or medical advice. Just to cover all my bases, I'm not licensed to professionally advise on anything at all. So this is just an educational talk to share some of the knowledge that I've gained working in the decentralized science field, and very basic principles so that you all have a chance to get this foundational knowledge that will allow you to explore the ecosystem on your own if you're interested, and make decisions about how much you want to engage, if at all. So the outline of my talk is I'm going to go over some basic terms. So if you've heard blockchain, cryptocurrency, Web3, DAO, decentralized autonomous organization, I want you to be able to know what those words mean and distinguish them from each other. And then I'll talk about themes underlying decentralized science and the trends that we're seeing in this space. And then I'll talk about the ecosystem and how it interplays with the traditional science ecosystem. So to get started with some basic terms, the technology that underlies decentralized science is called distributed ledger technology. So this is a shared distributed ledger technology in general is any kind of shared database where all the users have a copy of the records and those records are kept in sync. Now, a lot of people use the term distributed ledger technology and blockchain synonymously, but there are actually differences, namely distributed ledger technology is the umbrella term, and then blockchain is a subcategory of distributed ledger technology. Now, I'm not a computer scientist, and you don't need to be a computer scientist to participate in the decentralized science movement, but I do think it helps to have a basic foundational knowledge of these terms and the technology that underlies the movement. So blockchain as a subcategory of distributed ledger technology, it's the most common subtype, and it stores the data in sequential blocks. That's where you get the phrase blockchain. So it's a chain of these blocks of data. And that makes it more tamper-proof. It's essentially, the word people use is immutable, meaning unchangeable, because all future blocks store data of the previous blocks, and because there are so many nodes or participants that have access to the ledger, it's impossible to go back and change a previous block, because then the database would know that the blocks are now out of sync because the copies of all previous block data are stored in the current blocks. So with that said, with that being the underlying technology, we can move into some other terms that you might have heard, which are blockchain tokens. So there are two main types of tokens, basically fungible and non-fungible. And this is a really bizarre word. And I laughed the first time I heard it and thought it had something to do with mushrooms. But what it basically means is fungible tokens are identical and interchangeable. The most common type is a cryptocurrency. And if you understand regular currency, you can understand cryptocurrency. And so what I mean to say is, if I have $1 and you have $1 and we trade those $1, nothing has happened. My $1 is equivalent to your $1. I could have $10 and you could take 5 of those dollars and give me 5 more dollars. There's no difference because each dollar is equivalent to every other dollar. Now, on the other hand, when you have non-fungible tokens, that's a unique digital asset. So types of non-fungible tokens, or NFTs, you might have heard that phrase. The most common type you'll see, especially in the media, are art NFTs. And so that's taking art as a digital asset. So maybe a digital painting that somebody did, and putting it on the blockchain and trading it. And because it's a unique asset, that means that if I trade you one piece of art for another piece of art, those are not equivalent. So it's unique, and that's what non-fungible means. But it doesn't just have to be art. Anything that can be seen as a digital asset can be made into a non-fungible token, or NFT. And some other categories of NFTs that have come up are intellectual property NFTs, otherwise known as IP NFTs, where access to digital intellectual property is bought, sold, and traded on the blockchain. So another term that you should be familiar with before we move on is how this all comes into play to form organizations based on blockchain technology. And the most common or most famous type of organization out there is called a DAO, which stands for Decentralized Autonomous Organization. The basic principles are that you have a token. You know, the last slide we talked about fungible tokens and non-fungible tokens. Most commonly, it will be a fungible token, so some kind of cryptocurrency where you can buy multiple. The more tokens you have, the more power you have in the DAO. But there are DAOs that exist based on NFTs, or non-fungible tokens, where everybody might have one unique NFT, and that actually gives them the right to have one vote in the community. And when you're in that community, and it might operate as a club or more like a company, having those tokens gives you co-ownership or co-stewardship of the operations and often the assets that are held by the DAO. Now, there are some tricky legal issues that come into play, and that's really a case-by-case basis. And since I'm not a lawyer, I'm not going to try to dive into those. But that is the basic principle. And the last thing that I want to comment on in terms of DAOs is that they are typically have very transparent operations, because you have to imagine that everybody taking part in the organization needs to know exactly what's going on so that they can vote with their tokens. So in contrast to maybe traditional companies where the information is often very siloed, in DAOs, in the ideal setting, the information is available to everyone in the DAO, or often to the general public at large. And so it's a very open, transparent way of organizing activity. So that brings us to the theory of Web3. And a lot of people are confused by the term Web3, hear it as a buzzword, and don't really know exactly what it means. And I really like this diagram from the A16Z's State of Crypto. And the way that they explain it, or the way that it's often explained, is that Web 1, for those of you old enough to remember, Web 1 is the first iteration of the internet, and it was basically read only. So if you wanted to disseminate information, you would make your own web page. I remember being a little kid and making my first web page, writing it hard-coded in HTML and sharing my ideas and a couple pictures. And you can visit other people's web pages and read, their content. Then Web 2 is read-write, and what we think of as the current version of the internet, where you can go onto a website that's operated by a company like Facebook or YouTube, and it's not just about reading their content. You're interacting and posting your own content, maybe purchasing things. There's applications. So it's this read and write ecosystem. Now, these iterations of the internet already exist, and The Web3 community theorizes that Web3 is going to be the next iteration of the internet, representing a dramatic departure, the same way Web2 is a dramatic departure from Web1. And what it adds, we already have read write, but what it adds is ownership. So, the icons that you'll see there are like Bitcoin and Ethereum. And the idea is that because you can own digital assets and have that ownership, written into the blockchain, that gives you a very different web economy, and that there's a way to distribute ownership across the whole community taking part in the internet. Whereas remember, if we go back to Web 2 and we think about, YouTube or Instagram or Facebook or Twitter, everybody on there, there's a huge difference between the users and the employees operating the company. Those are not the same groups of people. The company is making the profits, even if the users are the ones that are posting the content and utilizing it. In Web3, the idea is that users and operators and profit makers are all the same group of people. So that brings us to the overarching themes of Web3, which are basically decentralization of power. So you can think of that in the diagram. Let me go back to the diagram for just a second. When you think about the diagram and you look at Web 2, the idea is that there's a centralization of power and wealth in the tech companies that are dominating the space. So even if creators are the ones posting all the content to YouTube, the vast majority of ad revenue goes to YouTube, the company itself. And YouTube has ultimate control over its content and can ban you and all of that. And, we can think about Twitter, for example, is in the news a lot lately, where it's very centralized. You can think of it as Elon Musk might make a decision, and then all of a sudden the entire world of Twitter has to comply with that decision. So that's one of the main themes of Web3, is decentralizing that. In other words, making it so there is no one central authority. It's community governed. The other theme is advancing technology. So, this is, again, Web3. It's supposed to be the next iteration of the internet. It's supposed to be, this is a dramatic advancement over what was possible before. So it's all about using currently available technologies to innovate industries and fields, and use those innovations to disrupt current systems, again, with this theme of decentralizing power. And the last theme I want to mention is this idea of transparency, and that yields also this idea of trustless, meaning that because there's no one central operator, because everything is distributed across the blockchain network, and because everything on blockchain is essentially public, you can trace any transactions online, all of them. You can see the entire history of all blockchain transactions ever, that you don't really have to trust anyone. If you log into your bank, for example, you kind of just trust that you're going to log in and your money's going to be there. And if it's not, then you know who to go to, to say, hey, Bank of America, where's my money? What happened? And there's like legal recourses, and you just assume that it's going to be fine, that, you can trust that person. So in the blockchain, there's a lot less of that. There's a lot less trusting of a central figure, because the idea is that it's built on the premise that you don't need to trust any central figure, because there isn't one. That everything is completely public, and it's not changeable, and it's not hackable, and what you see is what you get. So those are the main themes. And now I know we're all here for science, so I want to, now that we've established the basics, I want to talk about how this plays into science. So if we think about these two themes of decentralization of power and advancement of technology, you can just ask yourself, what do you think the main interests would be in the scientific community? Oh, I see that I have in the chat, how should we ask questions? I think that's for the organizers, right? Let me see. Okay, I don't see anything in the chat, so I'm just going to open my window again. Okay, so anyway, to continue, so we're thinking about these two main themes, and you can just ask yourself, you don't need me to tell you, who do you think are the central powers in the scientific community? Who do you go to when you need something? Who do you complain about when you can't get what you need? A lot of times it's going to be, the central powers are probably in your mind, publishers, universities. Publishers obviously control what your data, how it's shared with the scientific community. Universities control access and your job, your research position. Governments are the ones issuing grants and making regulations, and then pharma a lot of times ends up controlling patents and intellectual property. And so those are going to be the targets of decentralization, trying to spread the power currently held by those institutions out a little bit. And the other theme, advancement of technology, think to yourself, then, when you're doing science, what are systems that you're encountering where you feel like they're dated, or even outdated? So a really common example that comes up is publication. Maybe back in the day when we all communicated in paper, hundreds of years ago, it made sense to package any scientific advancements in written articles, packaged in issues of journals that are then distributed to subscribers. But nowadays, and I'm sure others have been talking about this in this conference, there are so many other ways of sharing data with each other that might be faster, more efficient, easier to archive and index and collaborate. And certainly there are a lot of efforts underway. There are all of these databases online for different fields where you can store information. Like in my research, I do a lot of genetics, and I'm constantly using the NCBI gene expression omnibus to look at all the other data sets. But we still rely on publication in pretty much an unchanged format from where it was a couple hundred years ago. Another one is reputation. If you've ever thought to yourself, I don't know how I feel about impact factor and H indices or H indices, I don't know if that makes sense as being the primary system for your reputation as a published researcher, that might be a target. If you've ever thought that it's difficult to collaborate, whether due to technological limitations or because the incentives aren't really there. We're incentivized for each lab to publish its own work, and there's often concerns about your work getting quote unquote scooped. We read in the news all the time that there might be two labs that are simultaneously racing to publish on very similar projects and essentially have been doing redundant work over the country. And, whoever publishes first will get the most glory, maybe, a prize or the patent. And that's, the culture that we're in. And then when you get to property and patents, there are all of these, especially when you get into the biomedical patent landscape. Again, I'm not a patent attorney, but I have done some reading and watched the news, and it's getting very difficult the patent landscape in biomedical research is getting increasingly complicated. Can you patent a gene? Can you patent technically no, but you can patent, a use of a gene modification for a specific indication. It's all getting to be a very complex system. and you know, there might be better ways to incentivize research, create a research economy that doesn't revolve around patents. And you know, if you've ever done work and thought, well, I'm going to publish this taxpayer funded research and eventually it's going to lead to a preclinical study and then a clinical trial, and then a pharmaceutical company is going to license the patent from the university, and they're going to make a profit, and it's never going to come back to me. That might be, again, one of those dated systems where you feel like we might be able to do something better. So those are main themes. Now, if we think about the academic science ecosystem, there's sort of this mouse running on a wheel situation where you in order to publish, in order to get your research funding from, you know, the NIH or whatever grant giving organization you work for, you know, they're going to want to see that you've published research papers. And before you can publish research papers, of course, you need to be, you know, have a research position so that you can be doing research. And to get the research position, or to keep your research position, you have to be able to demonstrate to your university that you are getting these grants, that your research is funded. Otherwise, you know, your lab will be discontinued, and it goes around and around and around. And it's important to point out because there are a lot of decentralized science initiatives that are trying to tackle different, you know, different points in this ecosystem. And I personally feel that they can often get stuck because it's difficult to make progress, do something innovative in one step of this wheel when you're still anchored in the other steps to existing systems. So to give you some examples, you know, there are a lot of projects in the decentralized science community using the distributed ledger technology that I talked about for, you know, open access data archiving and indexing. There are there's a DAO operated journal. I know of one, there might be more now, you know, where it's not a journal that's published by Springer Nature or any of these big publishers. It's actually operated by a internet native community. I've seen some protocols for tokenized peer review. And so that means that there would be incentive structures in the form of tokens. It might be a cryptocurrency, it might be some sort of reputation token or DAO token, but some kind of token incentive to provide peer review. And I personally think those are particularly interesting because I've seen a lot of chatter in the scientific community about people getting a little fed up with all of the free labor involved in you know, the expectation of doing things like peer review that doesn't actually feed into any you know, any rewards at all, whether it's reputation or financial rewards. So having the ability to incentivize peer review might help solve some of these issues that we're seeing with just not being able to find peer reviewers anymore. But and then in terms of research funding, there have been projects, there have been biotech DAOs. So that would be and I will show you an example of a biotech DAO before I finish up. So I'll explain that in a following slide. Quadratic funding is an interesting blockchain-based mechanism. It's kind of like crowdfunding, but basically you get major donors coming in and committing hundreds of thousands of dollars to a pool. And then you don't have a committee at the top deciding, you know, which applicants get a certain amount of money from that pool. What you actually have is the whole community coming in and voting. And the way that they vote is by making small donations. And then this formula, you can look it up later if you just Google quadratic funding. This formula comes in and determines how much of the large sponsor pool is going to go to each applicant based on how many people in the crowd have donated and how much each one has donated. And it's more important to have a lot of people donating a small amount than to have a few people donating a large amount. So it sort of is that decentralization theme again, giving the power back to the community to decide where the funding should go. And then, like I said before, another application is to sell biomedical intellectual property as an NFT. So I have seen some projects making IP NFTs with biomedical data. And so I was just laughing at the comment, the hamster on the wheel. So I'm almost done, but I just want to comment that, you know, decentralized science as a movement, as a field, it's very hard to describe. There's a lot of different people doing a lot of different things, and I think there's a wide spectrum. So if we look at those two main themes of, you know, decentralizing power, having a decentralized organization, and then you know, the technological advancement and building a scientific system based on blockchain technology, I think there are projects choose sort of which theme they want to rely on more. So there are some projects you'll see. So for example, on the decentralized side, there might be a DAO, again, that's an internet native community that votes on decisions and has co-ownership like a co-op. There might be a DAO that's operating a peer-reviewed journal. Now that journal might not be doing anything to do with blockchain. You know, the DAO might not even have a token on the blockchain, but they are aligning with this ethos of decentralization, community ownership, community decision making. So they might not store their data on the blockchain. They might not vote on the blockchain. They might not be researching anything to do with blockchain, but they are just more aligned with the decentralized theme. On the other hand, all the way on the other side of the spectrum, there might be members of the decentralized science community that are really focused on the technology itself and aren't really so focused on the decentralization. So I've seen traditional, totally centralized companies with CEOs and CFOs and COOs, you know, operating companies that provide products or services to, you know, to help facilitate, you know, decentralized science progress. So one example I've seen is a company operating a marketplace for biomedical IP NFTs. And again, they're not really so much about the decentralized ethos. They're just a traditional company that's going to profit off of the blockchain technology. But most projects exist somewhere in the middle, more or less decentralized, more or less something to do with blockchain technology. So you might see a blockchain-based peer-to-peer archive for large scientific data sets. And you know, it's peer-to-peer, so it's completely, and it's a protocol, so it's completely decentralized. There's no one person or one entity maintaining the server that you need to ask for permission from. So it's decentralized, and of course it's taking place on a blockchain-based data structure. So you know, so it also has something to do with blockchain technology. So most are somewhere in between, but that's why it's very difficult to define this movement, because it is a spectrum. So the last thing, I believe this is my last slide, and I just want to give you one example. So the example that I'm most familiar with, because I've actually been a part of one of these organizations, is a biotech DAO. And so the basic principles of how this works is, one, so you'll see the treasury icon is the vault, the bank vault. So the DAO, this organization, raises funds for its treasury by selling governance tokens. So people come in, they pay real money in exchange for getting these tokens. And you know, in the second step, the DAO members can use those tokens to vote. That's why they're called governance tokens. So they can use those tokens and vote to decide which research projects will be funded. So the community gets to decide, you know, where the funds of the treasury will go. And then once you get a project that's been voted yes, the DAO treasury takes some of that cash that it got from the sale of its tokens, and it transfers it to, you know, the researcher or company, whatever, in exchange for contract, you know, for owning the intellectual property, so that if whatever IP is born from that project, then it's, you know, owned by the community. And the way that worked in this specific biotech DAO that I worked in is that if there's any return on investment, so if they generate intellectual property that they eventually license to, say, a pharmaceutical company and get a return on that investment, that money goes back into the DAO treasury to fund future projects, and so it's supposed to be this self-sustaining cycle, ideally. So I hope that helped give a basic introduction to the field of, that was meant for people who had not encountered, who had not really understood Web3 before. And I just wanted you to be able to understand the terms. I'm not necessarily advocating for or against any of these approaches. It's just something that I wanted to explore so that I, would be knowledgeable about this ecosystem and could make informed decisions about it. And I just want the same for all of you. So I have my contact information here. I want anyone to feel free to contact me, with questions, even after this. And I have some suggested searches. If you were listening to on one of my previous slides and thought, oh, a DAO operated journal, I want to check that out. I have listed examples that I'm familiar with of each kind of organization or protocol. And I just want to do a tiny plug for my organization, which is new. We're not totally incorporated yet, but we have a grant. This is very exciting, and it's for Web3 Women in Science. And that's because, if you know anything about science and you know anything about crypto, there's underrepresented communities in both. Women are underrepresented in hard sciences and in crypto. So when you get decentralized science, which is the union of those communities, then you get kind of an underrepresentation squared effect. So I've been in meetings with, Zoom meetings with 20 people, and it's just me and 19, 25-year-old white guys. And so I just think that we should have more diversity in the space, regardless of how it ends up. And that's why I founded this organization. Thank you. Again, I can't hear anything, but if somebody could tell me in the chat whether I'm supposed to stop sharing or do I check the, hold on. Could someone tell me if I'm supposed to answer the questions in the chat, or if I'm supposed to stop talking because my time is up? Can someone
talking if you can? Can you talk, Ariella? Oh, there you go.
I'll just read this question and until someone tells me to stop talking. So I see there's a question, especially after the recent crypto turmoil, my enthusiasm about Web3 has cooled down somewhat. You're not the only one. Isn't a problem with DAOs that the richest people in terms of cryptocurrency tokens end up deciding? Isn't it more like a plutocracy than a democracy? If I make a large acquisition of tokens, couldn't I end up deciding where the whole pie goes? And it might be to myself. Yeah. So that's all very fair. There are ways to, let me take it one step at a time. So the richest people get the most votes. Sometimes, you don't have to have a linear system where 10 tokens means 10 votes. I've seen systems put into place where it's more exponential, or there might be a cap. Like the most votes you can have is 5. So you'll never have more than 5 times the voting power of someone else. But more often it'll be something like I said, where it's exponential. So maybe, 1 token is 1 vote, but 100 tokens is 2 votes instead of 100 votes, something like that. And like I said, there are systems where it's not based on finance. So you could have a system where your scientific reputation, which has been linked to your previous contributions with peer review or publication, actually earns you reputation tokens, and you use that to vote. So it doesn't all have to be financial, but there are definitely DAOs that do function as plutocracies. Absolutely. And you make a good point. There's in blockchain organization.
Have we lost Ariella?
It seems so.
Yeah.
Because we are using this centralized platform. Web3 screencasting service.
Yeah, that's the problem.
I can hear, but not see you, Hamid. I think your camera is possibly off or not working.
I can see Hamid.
Oh, okay. It's just my okay. The wonders of Web3.
Awesome. Okay. Any other questions for the chat? Ariella, are you with us? No, she can't hear us from there anyway. Any more questions? If you got any more questions, please put them in the Q&A. We could share those with Ariella in some other way. So Francesca and Gareth, do you have any comments on what Ariella was talking about?
I was just interested to note that there are some increasing pushes from funders. Ariella was mentioning funders and requirements at the end there. And for those of you in the US, I was just doing a quick look at the US NIH applications for funding received after the 25th of January 2023. There is a new data management and sharing policy which requires you to think about this in advance and have some put in for funding to allow you to share things. So how much it costs to set up something, to do a nice blockchain thing like was being recommended, I don't know. But there are some interesting things about open science more generally, I think, and trying to make things available. And Ariella's just posted in the chat that the curse continues and her laptop has died, so I don't know what has happened there.
Such a shame. Francesco.
I just want to tell her if she can hear us. Thank you for the talk. It's very thought-provoking. As I said, I was very enthusiastic about the idea. I organized together with the reproducibility study group also a virtual seminar in ISMRM about that. I am, but recently I got some information that made me reassess a little bit the situation, and it's always. I hope I will be able to catch up with Ariella offline and chat a little bit more.
So Mariella is being able to type into the chat by the look of it. So if people want to ask her questions there, it may be possible.
So there's a question here. Is there any scientific journal already using decentralized peer review? I don't know if Ariella's seen that. Any other questions? Anybody want to?
Maybe about decentralized peer review, something that also ties in a little bit with my topic. It's not using blockchain, but there are services where peer review is open and can be encouraged by multiple parties. So it's more a Web 2 approach, of course. But I think today there is pub peers was mentioned regarding the possibility of commenting about any paper online by the public. I think the more open peer review options, the better.
Yeah, so Ariella answered that one. The only journal she's aware of is Talon Dow's Journal of Decentralized Work. Ariella's also writing, Springer Nature has donated funds to research this. It's still so new, I'm not sure the protocols are ready. It seems like a fascinating field though, going forwards. Cool. Okay, any other comments? Anything else anyone would like to say? Anyone want to come on stage and say anything? Or we've just got a couple of minutes left. I think this has been a really, really interesting session. I'm sorry for the technical difficulties, but hopefully everyone's enjoyed this session anyway, and all the contributions the speakers have made. I'm sorry one speaker had to wasn't able to join us today. That was Nicholas Panettiere from Flywheel in the US, who was going to talk about QC with real-world data at scale. Hopefully, we can see his presentation again in the near future. So the discussions will continue after this session in GatherTown. The recording of this session will be made available on YouTube with captioning. And please go check out the program for the next session you'd like to join. The next one today is in about an hour on MRI hardware for everyone, which looks fantastic. So thank you all so very much for joining us, and enjoy the rest of the event. Cheers. Bye-bye.
Thank you.